Hello and welcome to episode 7 of the Game AI Mastery series in Unity C#. We're going to continue the work that we started in the last video. We're going to create a behavior tree component. First, we have to understand what this behavior tree component does. A behavior tree component takes care of a root task. It's responsible for setting the owner of that root task, of calling awake and then start on it. Then in the update method, it's responsible for calling update on it. So this is a very basic behavior tree. Here, all you have to do is set this root task to something like a utility selector or a parallel sequence or any task you want. So for example, we can set the root to a new utility selector and then create our behavior tree here. With this basic implementation, there are a few problems. For example, if you want to add this along with other scripts in the AI controller object, you'll have to make sure that the root task is defined before calling these methods. So for example, what we can do is call them in a start method, and then let the other scripts create the root task in the awake method. But that's too restrictive. So what we can do is actually call this code in the update method. However, we don't need to do this every frame. So we're going to use a boolean if has awaken. We're going to do this. And then we're going to set the has awaken to false. This way, the other scripts can define the root task either in the awake or start method. And when they do, we can initialize the root task here and update it down here. Now we have a second problem. When we call the update method, what if the root task has returned a success or failure? So we need another variable that we will expose in the inspector to tell us whether we should restart the behavior tree or not. So about creating this root object, what if we don't want to add another script on the AI controller object to create the root task? What if we want to do it through a scriptable object? In this case, we can create an abstract scriptable object called external behavior tree, which will have an abstract method that will create this root task. So any class that inherits from external behavior tree will have to define this method. Here we can add an external behavior tree variable. And right here, right before initializing the root, we can say if the external behavior tree is not null, then we will use its create root method to create the root node here before initializing it. Okay, now let's look at my actual implementation of the behavior tree component. Here we have a bunch of variables, restart when done, external behavior tree, data.
It is pronounced data.
And we'll discuss what data is shortly. Has awaken. Here we have our root task and a restart integer just to keep track of how many times the behavior tree has restarted. So in the awake method, we set has awaken to false. Here we take care of drawing the gizmos on the root task. Now let's look at the update method. If has awaken is false, we're going to call an awaken root task method and then set has awaken to true. Here, of course, if the root is null, we return. If the root status is inactive, we return, we do nothing. And here we call the update method on the root and get the status. If the status is a success or failure, we check if restart when done is set to true and then call restart on the root and increment the number of restarts. Otherwise, we set the root status to inactive. In the awaken root task method, if the external behavior tree is not null, we're going to set the root using create behavior tree. And this is the definition of our external behavior tree, which is a scriptable object. It has a create behavior tree method that returns the root task. Create behavior tree is more expressive than just create root, so we're going to call it that. Making this method abstract will force child classes to implement it, so they have to implement it. However, for the create data method, it's optional, so we set it to virtual. The child classes can override it if they want, but they don't have to. If you don't understand what this means, it's okay. We're going to explore behavior tree data and shared variables shortly. So back to our behavior tree component. So here, if the root is null, of course, we return. And finally, we set the owner of the root, we awaken the root, and we start it. Instead of just setting the status to inactive, I'm going to actually use task.stop. This is more appropriate. Let's peek into the definition just as a reminder. So the stop method is also going to set the status to inactive and call its onExit method, and will check for errors. So this is good. It's better to do it that way rather than just setting the status directly. to understand how tasks can communicate with each other, i.e. pass data along, let me show you a simple programming exercise, which could be insultingly simple for some of you, so bear with me please. Let's say we have two classes, class A and class B. Both have a public float speed. Somewhere else in the code, we create an instance of A and an instance of B. Let's say we set A.speed to 10, then we set B.speed to A.speed, and then we set A.speed to 20. In this case, what is the value of B.speed? Is it equal to 10 or is it equal to 20? The correct answer is, of course, B.speed is going to be equal to 10 because speed is a float and floats are value types. So how can we change the code so that B equals 20 at this point, which will make the speed variable shared between A and B. So whenever A changes the speed, it will also change in B. In this case, we need to wrap the value inside another class. This is also called encapsulation. Let's call the class shared float. It has a value of type float. Now in the classes A and B, instead of having a simple float variable, they're going to have a shared float variable. Since this is a class, we need to instantiate it. This code will no longer work because we can't assign a value to speed directly. We have to say speed.value. With this modification, now B.speed is going to be equal to 20 since both A and B share the same reference to the same shared float instance. We can actually assign a float value to speed by adding this method, public static implicit operator, shared float, and it returns a new shared float with a value as parameter. Here we need to define this constructor. So here we can simply say A.speed equals 10f, and here A.speed equals 20f. This only makes the syntax a little bit simpler. However, it doesn't change the behavior of the shared float class. Now in our implementation, we don't want to implement a separate class for each value type. We don't want to have a separate shared bool, a separate shared float, a shared string, etc. So what we do is we use generics. We define a shared variable with a generic type t. We give it a name property and a value of type t. And we define a couple of constructors. Then we define our implicit operator down here. And now for the sake of simplicity, we can define a shared type for each value type. So here we have shared bool, shared float, shared int, string, vector3, vector2, transform, game object, and color. Each will inherit from shared variable with the appropriate value type. However, for our implicit operator to work, we have to define it for each child class. We'll also need a shared variable list, which is a list of shared variables. It also uses the generic type t. We can get the list using list as read-only, which returns an iRead-only list. Then we have methods to add an element, remove an element, and get an element by name. Now about BehaviorTree data. It's a class that has a list of variables for each type. So we have a list of NPCs, a list of floats, booleans, ints, strings, vector trees, vector choose, transform, and game objects. Now, if we go back to external behavior tree, the behavior tree component will call this method and will give it a data instance, and the external behavior tree can add its own variables to this data instance. Now let's go back to our behavior tree component. Let's go to the awaken root task method. Here when we have an external behavior tree, we'll call create behavior tree, which will create the root task. Then we call external behavior tree dot create data with our data object, and our data object is defined here. In AIController, we had a utility selector. So basically, we forced our behavior trees to have a utility selector as a root task. However, now that we have a proper behavior tree component, we no longer need to do this. So I removed all references to utility selector from the AIController script. So now the responsibilities of the AIController are even more limited. And that's exactly what we want. This is actually very good. The AIController is now like a bridge between our game code and Unity's navmesh agent. So the AIController script will subscribe to the set destination action and will set the destination on the navmesh agent. We already did this in the previous videos. However, now I've also added a has path to destination. Let's go into the NPC script. We use a system func because Unity actions cannot return a value. In the AI controller, when setting the NPC, we unsubscribe from hasPath to destination on the old NPC, and we subscribe again to it on the new NPC. And this is the callback that we're going to be using. When a navmesh agent doesn't find a path, the path status property will be equal to navmesh path status dot path invalid. Using shared variables is not the only way to make tasks communicate with each other. We could create a script here in the AI controller object, and in the onAwake method of tasks, we can access that script and we can have all the data we want over there. However, this makes our tasks dependent on that script. Ideally, we want our tasks to be as reusable as possible, and shared variables make that possible. This concept of having a script or a data container in general, where tasks can read and write data. This is called a blackboard, and there are a lot of ways to implement blackboards for behavior trees. I personally like to use shared variables, but in some particular cases, we'll create scripts that the tasks can access and modify. Let's create a custom inspector for the behavior tree. Let's create an editor folder, and inside of here, let's create a script called BehaviorTree editor. Make sure to use the Unity editor namespace. So our BehaviorTree editor will inherit from editor, and we need a custom editor attribute of type BehaviorTree. First, we define a boolean show data. We'll see what this does shortly. Let's override the onInspector GUI method. Here we're going to draw the default inspector, and we're going to draw our custom controls below the default inspector. Here we get a reference to our behavior tree. Then we add some space in the inspector, and we add a button called OpenViewer. This will call the show window method on the behavior tree viewer. We'll also see this shortly. Then we add some space. Then we create a foldout for the data. So this is where we use the show data boolean. Then if this boolean is true, we're going to draw the data property. We also need to increase the indent level just to make it look better on the inspector. And for good measure, if GUI has changed, we set the behavior tree to dirty using editor utility.setDirty. Now let's define our drawData method. So it will take a behavior tree data object and we'll draw it. Let's set GUI.enable to false. This will disable input on the controls and fields that we're going to draw. Then we go through each list and we draw the appropriate field. So here we go through the NPC list and we draw an object field. For object field, it's important to set the fourth argument, which is allow scene objects. But it's completely irrelevant here since we don't allow input. For each element on the float list, we create a float field. For the booleans, we create a toggle. For the integers, we create an int field. For the strings, we create a text field. For the vector trees, we create a vector tree field. Same for vector 2. For the transforms and the game objects, we create an object field. Then we set GUI enabled back to true. By the way, in the behavior tree data class, here I created lists for the most common types. You can add types from your game here, so whatever you need. We may add more classes here if we want. Now let's make the behavior tree viewer. For editor code in general, you have to put it in an editor folder. However, for example here for the behavior tree viewer, I didn't put it in an editor folder. If you have editor code in a non-editor folder, you have to encapsulate all your code between if Unity editor and endif. We've already seen this before. Okay, so let's get started. Let's implement a behavior tree viewer. Our behavior tree viewer derives from editor window. Let's define some variables that we're going to need. First, we have a scroll position, since we're going to add a scroll view to put the behavior tree in. Then we have a reference to our behavior tree here and also the root task. And we define an indent size and a depth variable. So the root task will be at depth 0. And then the children will be at depth 1 and the grandchildren will be at depth 2 and so on. Then we define a show window method and we add it to the editor's menu bar using the menu item attribute. In here, we're going to get window behavior tree viewer and give it a title. That's all we need to show the window. How I want the behavior tree viewer to work is that you select an object and it displays the behavior tree on that object. We also need the behavior tree viewer to update itself every frame. So we subscribe to both selection.selectionChanged and editorApplication.update. Let's define these two callbacks, onSelectionChanged and onUpdate. So in the onSelectionChanged, if the active game object is null, we do nothing. And if not, we're going to get a BehaviorTree component from that object. If we find nothing, then we're going to get the object from its children. If the BehaviorTree is not null, we're going to set our BehaviorTree variable to the BehaviorTree we found, and we're going to set the root to bt.root. And this is the onUpdate callback. If root is null, we're going to call onSelectionChanged that we defined here, and then we're going to repaint the window. Remember that our BehaviorTree is only created at runtime. So with this selected, if we run the game now, in our onUpdate method, the BehaviorTree will be set to the BehaviorTree on the selected object. Now let's define the onGUI method. This is where the window actually draws the BehaviorTree. As I said in the beginning, we're going to use a scroll view. So we call editor GUI layout.begin scroll view. We provide it with our scroll position, and we assign the return value to the same scroll position variable. We set our depth to 0. If the root is not null and the BehaviorTree is not null, we begin a new row using begin horizontal and end horizontal, and we draw a label where we display BehaviorTree and we display the number of restarts on that BehaviorTree. Then we call a drawTask method with the root as argument. Otherwise, we draw a label that says select a BehaviorTree object to begin. At the end, don't forget to call endScrollView. First, we define a method called getTaskTextColor, which takes a task as argument and returns a color. If the task is running, the target color will be green. Otherwise, it will be set to the normal text color. We also assign a color if the status is a failure or a success. However, this will not be displayed since in our code, as soon as the task returns a failure or success, it is usually stopped. For the utility selector, we'll draw the utility value for each of its children. For this, we use a method called drawUtilityLabel, which takes a task. First, we save the GUI color. Then we set the color to yellow. Then we draw a label field. We round the utility value to 1 decimal point, just for good measure. Then we restore the GUI color. Now let's dive into the drawTask method. So the drawTask method takes a task and then a boolean drawUtility. So if this boolean is false, it will not draw the utility label. First we save the GUI color and we set the GUI color to getTaskTextColor. We're going to check if the task is a composite. With this syntax, then we're going to call a drawComposite method. If the task is a decorator, we're going to call a drawDecorator method. Otherwise, this is either a condition or an action. First, we call a beginTask method. We draw a label with the full name of the task. Then if drawUtility is true, we call drawUtilityLabel, and then we end the task. And finally, we restore the original color of the GUI. Let's see what beginTask and endTask do. So in beginTask, we begin horizontal, and we draw a horizontal space with indent size multiplied by depth plus 1. And in endTask, we call end horizontal. Then we draw a colored box, which will be green if the task is running, and gray if the task is not running. With editor GUI.drawRect, we draw the rectangle. Then we draw a sort of arrow just to help visualize the hierarchy a little better. So the arrow is made of 2 boxes or 2 rectangles. We should normally draw an icon here, so this is just a quick fix. Now let's see the drawDecorator method. We call beginTask. And then we draw a foldout. Remember that we defined the viewer show foldout in the task class. This is where we use it. If drawUtility is true, we draw the utility label, then we end the task and we increment the depth. We only draw the child task if the viewer show foldout on the decorator is set to true. Then we decrement our depth variable after drawing the child. Now for drawComposite, we do the same thing we did here for the drawDecorator. And for each child task, we call drawTask on it. And we only draw the utility label if the task is a utility selector. So with the is keyword, we will know if a task derives from utility selector. That's it. Now we can visualize our behavior tree. We can fold in or fold out branches of the tree. To allow us to better visualize the behavior tree as a whole, I want to talk about a small detail that I missed last time when we talked about the task class. So we are in the task script. I said that we should set the name to virtual and that child tasks can override it. However, what should be overridden is rather the full name. This property returns the full name in a certain way. And actually, this is what we should give the child tasks the opportunity to change. In the wait action, I've overridden the full name property to display the remaining time. And remember, for the remaining time, it is our timer private variable here. So we round it up to 1 decimal point. Then we display it next to the name. So if the name is null or empty, we display the type name, which is wait, plus the number of remaining seconds. If timer is 0, we set the timer string to an empty string. And then if the wait action has a name, we display the time next to that name. And then we display the type between parentheses. This is a great way to increase visibility of your behavior tree, which helps us read the viewer even better, so we know exactly what's going on. Here I have an NPC with the AI controller and a behavior tree. It has a Wander external behavior tree. So this is our previous Wander action. It takes care of everything. Now we're going to break it down into single tasks. This is a behavior tree that achieves the same result as our Wander action. We override the create behavior tree method and we create our behavior tree here. So the root task is a repeater. So we set up the repeater and we return it. And then for the create data method, it's empty for now. We'll see how this works and we'll see some more examples of behavior trees. Until then, see you later.